Hi everyone. I just want to review a little bit of what we talked about in the previous section on the simple valence bond model. Remember that the idea of the valence bond model is you can represent a chemical bond by looking at the two atoms that form a particular bond and thinking about what orbitals in the atoms themselves that contain only single electrons and combining those orbitals together to form the chemical bond. Okay, so we talked about the different types of bonds that could be formed as a result of overlapping these orbitals in the different atoms. But here what I want to do is just show an example of how you can use this to predict or explain the bond angle that's observed in the molecule hydrogen sulfide. So if you look at the energy electron configuration of the sulfur atom, you notice that it's going to have this particular configuration: 1s2, 2s2, 2p6, 3s2, 3p4. And the 3p4 here, of course, is the highest energy orbital in this particular atom, and that's listed here. Now, if you look at this, you can clearly tell that there's only two orbitals with single electrons. So what that means is these two orbitals can then be used to bond with orbitals from other atoms that also have single electrons. Now, in the particular case of H2S, of course, what we're going to do is overlap each of these p orbitals with one s orbital from hydrogen atoms. So, in fact, the bonds that are formed, they're going to be two bonds because there are going to be two single electrons here. They're going to be two bonds, and the bonds are a result of overlaps between these three p orbitals, each one of them with a 1s orbital from hydrogen atom. So as a result, there will be an SH, overlap in one, and there will be another SH overlap. So I'm going to show you here a little animation that shows how this bond, these two bonds are formed. So here, by the way, this particular representation here is the representation of the sulfur atom. And remember that this is basically the representation of the p orbitals that are in sulfur. So remember that p orbitals have these bilobal shape like a dumbbell. So you have one p orbital here, top and bottom, on the blue axis. You have another p orbital on the red axis, and of course you have another p orbital here on the green axis, which is directly coming out towards you, and there's another one that's pointing to the back that we can't see right now. But those are the three p orbitals. But remember, one of those p orbitals is already filled with a pair of electrons, so only two of them are going to have single electrons in them, and these two are the ones that are going to make a bond with the hydrogen atoms that are going to come and join up and overlap their orbitals with the sulfur orbitals. Okay, so I'm just going to play this video a little bit and show you the animation. And one of the things you're going to see is here's your hydrogen 1s orbital is coming in, and it's going to overlap with this one of the p orbitals that contain that single electron, making one bond, right? So there's one bond right here. That's one of the H2S bond, right? And the other one, of course, is going to be another p orbital. So this molecule has just been rotated 90 degrees. And here's another 1s orbital coming in. And there you go. Now you have your two bonds right there. I hope it's clear here. There's one bond right here, and there's another bond at the back there. Okay? Now let's see if we get a perspective where we can see this a little bit more clearly. But hopefully you can see as this molecule is being rotated that here's one bond, and here's the other bond. One is on the green axis, and the other one is on the red axis. Now you can tell that one of the things you can tell right away, if you remember back from discussion about quantum mechanics and p orbitals, is that p orbitals are perpendicular to each other. They lie exactly on the Cartesian coordinate axis, so x, y, z, and those axes, of course, are perpendicular to each other. So in other words, we would predict that the angle of this H2S molecule, right, which is this angle right here, this bond angle, should be 90 degrees because it's exactly where the p orbitals are oriented. And in fact, when we experimentally measure the bond angle in H2S, we find that indeed the angle is 90 degrees between the HSH atoms. So as a result, this is of course a demonstration that the valence bond model is valid in terms of making predictions of structures. However, it turns out that this works for many molecules, but for certain types of molecules, this approach actually doesn't work. This fairly simple valence bond model approach doesn't work as well. Now, what example would be molecules that, for some reason, if you're just using this simple approach, would not be able to predict the actual angles or the actual structure that's observed in experiment? An example would be the CH4 molecule, okay, which is methane, right? So we talked about methane throughout the semester in various contexts. Now we're going to mention it in the context of the valence bond model. So if you look at methane, we know that methane has a formula CH4, which means there are 4 CH bonds, right, in the molecule. And we know from Vesper and from drawing Lewis structure before, you know that the bond angle of the methane molecule, the HCH bond angle, all 4 have the same value, and that value is 109.5 degrees. Remember that this is our tetrahedral structure, methane. And just a reminder of what that actually looks like. This is your methane molecule, here's your carbon, and here's your 4 hydrogens. This angle here is what I'm talking about, 109.5 degrees. Okay. Now let's take a look at how we would predict a molecule that will be formed by carbon and hydrogen using the simple valence bond model, the one that we just applied earlier to the H2S molecule. If you look at methane, or if you look at carbon and hydrogen, I should say, the simple valence bond model would have predicted that a molecule that's formed by carbon-hydrogen would actually have 2 carbon-hydrogen bonds. In other words, the formula would be CH2 instead of CH4. And then each HCH bond angle would have been 90 degrees. So you might ask, well, how did I come up with these numbers right here? It's fairly straightforward. Basically, I'm doing what I did earlier with the H2S molecule. In this case, I put the electron configuration of carbon. And as you can see in the carbon electron configuration, only 2 electrons are available for bonding, right? Because these are the 2 single electrons. And of course, what we would do if we want to envision bonding between carbon and hydrogen, we would overlap this orbital right here, the px orbital, with the 1s orbital from hydrogen. And then we would overlap the other p orbital containing single electron, which is the py orbital, with another hydrogen atom, another 1s from another hydrogen atom. But again, based on the discussion we just had about p orbitals, these 2 p orbitals are going to be perpendicular to each other. If they're perpendicular, that means that the angle between the HCH would be exactly 90 degrees. And that's why we got this 90-degree value. And that's why we got 2 CH bonds, because there's only 2 single electrons. Now, this is clearly wrong because we know that this molecule doesn't exist. What exists is this molecule, the CH4 molecule. So then the question is, how do we account for this type of discrepancy? How can we adjust the theory, which is the valence bond theory, in such a way that it would help us explain the existence of methane? To do that, you need to come up with an additional variation, basically modification on the valence bond theory. And the idea here is that sometimes you can use that simple model of valence bond theory that I just talked about before for the H2S molecule, but sometimes you need to come up with a modified version which incorporate this concept called the hybrid atomic orbitals. Okay? So the idea is as follows. If we were to only use the standard atomic orbitals, standard here refers to the s, p, d, f orbitals that we talked about, that you're familiar with at this point, we're not going to be able to explain how certain molecules exist, like CH4, methane is one example, but you'll see some other ones later. Beryllium dichloride, BeCl2, we know that's a linear structure, 180 degrees. BH3, which is a trigonal planar structure. We're not going to be able to explain any of these structures if we're just using this SPDF standard atomic orbitals. In order to model these bonds that exist in these molecules, we can't just envision that the bonding is an overlap between one standard atomic orbital with another standard atomic orbital. what we have to do is we have to imagine that the bonding occurs because of overlap between one hybrid atomic orbital in one atom with maybe a standard atomic orbital from another atom, or an overlap between two hybrid atomic orbitals. Okay? So it's not, so then, in other words, the way you're going to use the valence bond model is there's three different ways you can kind of envision a bond. Sometimes a bond is an overlap between two standard atomic orbitals. That's the one that we've talked about so far, right? That's the one that I mentioned in the previous set of videos when I talk about molecules like H2, where this is just two 1s orbitals. These are both standard orbitals, they overlap. Or HF, where there's an s and a p overlap, you know, or F2, where there's a p and p overlap. Okay, so those are all standard types of overlap. In this set of videos, we're going to talk about overlaps between one, a hybrid atomic orbital from one atom and then a standard atomic orbital like an s or a p from another atom, or we're going to have overlaps between two hybrid atomic orbitals. Now the question then is, what are these hybrid atomic orbitals? Okay, we're going to talk about this in the next video, because I do want to spend some time talking about exactly how you can construct these hybrid atomic orbitals.